Okay, this is the second topic for this week's module. This mostly will be focused on echo train sequences. I'll talk about multi-echo spin echo and fast spin echo. So what's the point really of using an echo train in the first place? Well, most of the theme here is on fast acquisition. So another reason or another way to speed up your acquisition is to use so-called echo train sequences. These can allow you to acquire an image in one shot, where a shot means one excitation. So you think of the spin echo sequence, and if you have a 90 and a 180, instead of going to another 90 for one shot, you just have 90, 180, and then 180, 180, 180, 180, continuing until you've acquired the entire image. And in that example, that would be called single shot fast spin echo. But the point is, for any sequence that you hear is single shot. For example, echo planar imaging can be single shot. There's only one excitation pulse. And so, for example, in echo planar imaging, you can acquire an entire image in under 100 milliseconds. So it's a very powerful technique. So what is an echo train in general? Echo train is just a series of echoes that are formed either by gradients or RF pulses within one TR. So here I'm just showing echo 1, echo 2, echo 3, and so on and so on. There could be 4, there could be 8. There could be really any number of echoes in an echo train, but the point is that usually an echo train means a certain number of echoes within one TR period. So what are some of the sequences which form echo trains? Rare. So I've talked about, I mentioned that in the beginning, or fast spin echo. Rare stands for rapid acquisition, relaxation, enhancement. Echo planar imaging uses echo trains. Multi-echo spin echo also uses echo trains. And I'll talk a little bit more about multi-echo spin echo and rare in this module, in this topic. So first, let's look at, go back to the plain old spin echo sequence again. So you remember that for every repetition, so here on the left I'm showing the spin echo sequence where we've acquired one echo, so we have acquired one line of K-space in one TR. And then the next TR, where we would have another 90-degree pulse and all of these ensuing waveforms, we would acquire another line of TR. So you can kind of get the feel that that's not very fast, right? Because what if we had, usually number of lines in X or in Y and X are 128. But really it's the number of lines in KY that limits how fast you can image. So imagine repeating this sequence 128 times. What people have done, excuse me, let me start over with that. So if you think about that, think about the conditions for a T2 weighted image. And to get T2 weighted contrast, you need a very long TR. So TR is usually around T1, 5 times T1, and some tissues have T1 of around 1,000 milliseconds. So the TR for a T2 weighted image, if you're going to use a plain old spin echo sequence, is on the order of about 5 seconds. So now if we have an image where the number of lines in KY are 256, then we have a scan that lasts for 21 minutes, and then again that's assuming only one average. So if the signal to noise wasn't good, then we would have to average more, and if we average just one more time and go to next equals 2, then we have a scan that's 42 minutes. So clearly there's got to be a better way to do that. Or clearly we need to find a better way, and people have done that. Other issues with long scans like this is that people don't like to lay in the bore of the magnet for very long, and so inevitably after around even just a few minutes, there's going to be the person might have to move their head a little bit, or they have to, maybe they'll take a deep breath. How you sigh every once in a while, you take a deep breath every once in a while. So after 21 minutes you're going to get some motion of the person, so you really want to try to make your scans as fast as possible, and that in order to minimize motion artifacts. So so I'll just show here one version of a multi-echo spin echo sequence, and what this is typically used for is you can generate multiple T2 weighted images, or you can generate multiple echo images, and from those images you can create a T2 parameter map. So for example, now what I've done here is I've taken that same pulse sequence, kind of just squished it down, or I just made the TE shorter, and then all I've done is I've added 2 more 180 degree pulses. Now I'm only phase encoding once, okay, but what happens here is if you add more 180 degree pulses and you only phase encode once, you can generate 3 different K spaces. Okay, and then so what that ends up doing for you is then you can generate 3 images that have different weighting. And to generate a parameter map, you would take the images from each of these, or on a pixel by pixel basis, and you could plot out the curve, the so-called, so the curve being, if I had a line, you see these signals here, the T2 envelope is from one peak to the next to the next. That's the T2 envelope. So by using these separate images, I can generate a map of T2. So it's kind of a picture of T2 per pixel. So this really it's still a slow method, but it shows some increased efficiency in terms of being able to generate more than one image, though the TR is still pretty long. So this brings us to fast spin echo. So now somebody, or actually quite a while ago, I believe it was in the mid-80s, came up with a way to, or had the idea that, well, we can have multiple 180 degree pulses, but what if we phase encode the echo from each pulse? Then we can more efficiently traverse K-space. So that's a general idea of fast spin echo, is using more than one 180 degree RF pulse to refocus the transverse magnetization to form additional spin. That's a typo there, spin echoes. And use the additional echoes to acquire more than one line of K-space per repetition period. So let's look at what that sequence looks like here. So what I'm showing here is spin echo 90, 180. We have slice selection, and then we have slice selection on 90, slice selection on 180, and we phase encode this echo. So this echo has been read out. So we have read out one line, and we have phase encoded it. So we've moved to a high value of KY here. We have this phase rewinding gradient because we're going to add another 180 here, and we're also going to phase encode that echo. So we have to rewind, or we have to cancel the phase that has been induced by this first phase encoding gradient, so that the next echo has phase that's independent of this gradient, because we want to phase encode this, so we want to be able to put the signal from this echo at a certain place along KY. So we can't have any phase from the previous phase and cogradient. Otherwise, this line in KY would not end up where we expected it to end up. So that when we reconstruct the image, in that case, if that were the case, if this line was not in the right place in KY, we would have artifacts when we reconstructed the image. So we can continue with this, adding another 180-degree pulse, and you can see what I've done is I've color-coded, so this echo ends up along this line of K-space, and this echo ends up along a lower version, because again your amplitude of your phase and cogradient is lower, still positive, so you're on this side. Okay, so we continue with that, and so on. So here, this is a common amount or number. Usually there are, maybe 4, 8, 16, or even 32 180-degree pulses. So that in one TR, what I'm showing here is that in one TR, you can acquire, although I'm not showing 4 lines, I'm only showing 3 lines of K-space, but there would be one more line from this last 180-degree pulse. In one TR, you can acquire 4 lines of K-space in this example. So what you've done compared to the regular spin echo sequence is you've increased your time, or you've decreased your scan time by 4. And in this example, the echo train length is, so echo train length is a very common term in terms of when you're speaking about the FSC pulse sequence. Echo spacing is another common term. Okay, so let me just see here. I'm trying to use this pen. Okay, so again, echo train length, or ETL, is a number of 180-degree pulses. ESP is the echo spacing, which is the time between 180-degree pulses. So the time from here to here. So this is ESP. Okay, this is the echo spacing here. And again, the echo train length is just the number of 180-degree pulses per TR. So let's look at how K-space is filled. This is very important by fast spin echo. So if we look at this first, what I'm showing is just a phase encoding gradient, and I've color-coded each phase encode step. And this is one TR. The next TR, I'm showing it the next row here, and this gradient has changed a little bit. Each one has changed a little bit. And the next TR, you can see that each one has changed again. So what ends up happening is for this echo, I'm showing here, this little text box says encodes echo number 1. So although these are changing, what the amplitudes will do is stay within a range of certain high values of KY, both near KY max and near KY min. And similarly with the second echo. So the second echo has intermediate values, which are a little lower than the echoes for number 1, or the K-space lines for number 1. So they stay around these regions of K-space. The third echo, so now I'm just going to call it mapping. So the third echo gets mapped into these regions of K-space. The fourth echo gets mapped into the central region of K-space. And that's very important, because it's the echo that gets mapped to the central portion of K-space that determines the weighting of the fast spin echo sequence. So you can change which echo. When you're at the console doing the imaging, you can say, I want the first echo to be towards the center of K-space. I want the second echo or the third echo. Depending on what kind of contrast you want, you change that echo number. So let's say, back to this example, we want our contrast to be based on this last echo here, echo number 4. Let me go back here. And if that's what we selected, if we said we want the 4th echo to be the one that's associated or mapped to the center of k-space, then that echo determines what is called the effective echo time. In fast spin echo, you don't have, you can't say what is TE, right? Because you have 4 or 8, you have several 180 degree pulses. You can't just say my TE is 20, because then you'd have to say, well, which, for which 180 pulse do you mean? Instead, what's done is, in rare and fast spin echo, the term is called effective echo time, because it's the echo that gets mapped to the center of k-space that determines the echo time, but it's really ineffective because it's an approximate echo time. And we can change that by changing which echo gets mapped to the central part of k-space. So here, on the second example in the bottom row, I'm showing that the first echo now gets mapped to the central part of k-space. So now the effective echo time here would be much shorter than in this top example. And in this top example, the image is weighted by the 4th echo. In the bottom example, the image is weighted by the 1st echo. So let's just look at a quick example here. So if we have an FSE sequence that has an echo spacing of 8 milliseconds and an ETL of 16, I've asked a few questions here. What is the effective echo time for T1 weighted imaging? Well, if you want T1 weighted imaging, right, you want your echo time to be short. So you should use the first echo to sample the k-space center. And if the echo spacing is 8 milliseconds, the shortest you can do, the shortest effective TE you can have is 8. So it's just equal. The TE effective becomes 8 milliseconds for a T1 weighted sequence. Now, if you were asked then which echo should be used to sample the k-space center for a T2 weighted image with this TE. So for T2, TE is usually much longer. Well, again, we have 16 echoes at our disposal. So if we want a TE of 102, we know that the 13th echo has a TE of 104 milliseconds, right? Because 13 times 8 is 104. So we're close, and that's close enough. And so that's our closest solution. So the 13th echo we would use in that case. Now if you wanted a heavier T2 weighted image, for example with a TE of 120 milliseconds, what would we do? We would use the 15th echo. Okay, so 15 times 8 is exactly 120. So what is the longest TE, or what is the longest effective echo time that the sequence can produce? It's just the echo train length, which is 16, times the echo spacing, which is 8. So we can get 128 milliseconds. Again, that's for an effective TE of 128, we would use the last, so the last echo would have the lowest phase encode gradient amplitudes. Would be associated with the lowest phase encode gradient amplitudes, so that echo is mapped to the center of k-space. And then in that case, we would have an effective echo time of 128 milliseconds. So I'll just end up here talking about some conditions for the sequence. And previously I showed you the timing of the pulses, but in addition to that, it's important that the phase of the pulses be such as this, where the first 90-degree pulse is applied along the x-axis in the rotating reference frame. The next RF pulse is applied along the next ensuing RF pulses. When I've said theta here, where theta is usually 180 degrees, they are all applied along the y-axis, and the timing must be 90 tau theta, 2 tau theta, 2 tau, and so on. Now, why are we changing the phase? Well, there can be imperfections in the refocusing pulse flip angle. So let's say the first 180 pulse although you want it to be 180 degree flip angle, it ends up being 177, and the next RF pulse is 182. And if that's the case, what can happen, there are other echoes that can be generated, and I'll just mention them briefly. These are called stimulated echoes, and but by alternating these signs, by having X and then Y, 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 you reduce the impact of those unwanted echoes. So that is really what is called the Carr-Purcell-Myboom-Gill condition. And I'll let you read this. There are two conditions, and I've mentioned them just briefly here. And these two, for a conventional fast-spin echo sequence, they must be adhered to, otherwise you will see artifacts in your image. So that's all I will talk about right now for rare and for fast-spin echo. If you have questions about this, please let me know. I will include the PowerPoint slides onto Blackboard, and we'll go from there in the discussions or email. Thank you.